Okay, happy Friday. Wow. If only you were that enthusiastic about the math. Okay, so notice next web work is due Monday at 6. It's short. Now, so these web works, you have to discipline yourself to investigate and get the most out of every problem rather than even if you just get it right. So it may be easy to get it right without really thinking through the problem. So that's where you have to take the initiative to really investigate and tear it apart and make sure you're understanding what it is about this problem you need to understand. So yes, sometimes the answers are just easy to get. You can move on to the next one, but they're all important problems. Okay, so that's just some advice. Okay, they're all valuable, and if you're just getting an answer and moving on and forgetting about it, then you're not getting the value out of it. Yes, sir. Oh, so I'm at 26. I'll change it. Yeah. So it's due Monday at 6. I'll change it. Okay. And then Wednesday, there's a web work due before class and a written homework. And all the material for that stuff is what we'll cover Monday. So you can look at it, you can go for it, but just warning that it may be unfamiliar because we'll cover it Monday. Okay. So that's that for homework. So there were a couple problems dealing with factorials. And I intended to take it off of today's homework, but the success on those two problems was very high, so it's okay that we just left them on. But now you saw that, and maybe you were wondering what it was, and so now we'll talk about that. And this will definitely be coming into play in the next couple of weeks, a really important thing. So factorial, so 4 factorial, this is not 4. Okay? This is 4 factorial, which means you start with the number 4, and then you multiply down by the whole numbers until you get to 1. So every factorial will end up multiplying down to 1, no matter where you start at. Okay? So you start with the number that's factorial, and so in this case it'd be 4 times 3 times 2 times 1. And so 4 factorial is the same as 24. Okay? So by definition, 0 factorial is not 0, it's 1. It's just a fact that you memorize. We could, if you want to come to office hours, we can have a conversation about why this is. But if not, it's a fact you memorize. 0 factorial is not 0, it's 1. Okay? And that's because when factorials start getting involved in other things, it ends up making sense, much more sense that 0 factorial equals 1 than 0. Okay, so that's just, you memorize that. Okay, so practice. Write out what this means and find the value. Go, write out what this means and find the value. So what number do you start with? 6. And you're going to multiply. You just keep subtracting 1 every time and multiplying down until you get to, always till you get to 1. A factorial is always down till you get to 1. How does 6 factorial relate to 4 factorial? Do you notice that within 6 factorial, some of you have, within 6 factorial is 4 factorial. In fact, every factorial for numbers less than 6 are in there. Do you see that? This is important. So when they start doing some math computations, bringing these together, that's an important fact. So every factorial less than 6 factorial, every factorial for numbers less than 6 are contained in 6 factorial, or they're a factor of, right? They're a factor of 6 factorial. All right, so that being the case, what would this be? So write out, someone said 3 factorial, it's 3 factorial. Okay, write it out. Write it out. And write it out in such a way that it shows the meaning, but doesn't break your hand, right? So how can you write that out so it shows the full meaning of that, but doesn't give you a cramp, okay? Can you do that? It's an important skill, right? Because I could have written 228 factorial over 225 factorial, and the same thing. We want to be able to write that meaning out without breaking your hand. So 28 factorial would be? It's easy, right? And then, yeah, so use this thing, and so on, right? And so on. And factorials always end at? So I'm going to write 3 times 2 times 1. They always go to 1. Every factorial always multiplies all the way down to the number 1. And then we're going to divide by 25 factorial. Which is? So notice we still can communicate the full meaning of factorial and not have to write out every number. So what does this equal? So notice, like we said, 25 factorial is part of 28 factorial. So when you divide, not subtract, right? Not subtract. When you divide, that all goes away, right? That's 1. All that goes away. The 25 factorial, that's part of the 28 factorial, can simplify to 1, and you're left with 28 times 27 times 26. Make sense? Okay, so these will come into lots of our sequences and series. Let's look at this. So here's a sequence, right? A sequence. 2i minus 1 factorial over 2i plus 1 factorial. So we want to start by rewriting that formula in terms of its meaning. So we can do some math here. So 2i minus 1 factorial. So the first number in the product is 2i minus 1. And then what's always the next number that you multiply by? So it's going to be 1 less than that number, right? So what's 1 less than 2i minus 1? 2i minus 2. Minus 3, etc. So this would just keep going. So we have no idea what I is, right? Or it's just be any number. But then when do we end? 3 times 2 times 1. So eventually we'll get down to 1. What about 2i plus 1? So the first number we multiply by is 2i plus 1. And then the next one we always multiply by is 1 less than that, which is 2i, then 1 less than that. Do you see how what we're doing here is exactly the same thing as what we did up here? Do you see that? So we're applying factorial exactly the same way we applied it up here when we just had numbers. Okay, then now we've got some math to do, right? What happens now in this sequence? Notice 2i here. What is this right here? That's the numerator, right? So because 2i plus 1 is a greater value than 2i minus 1, 2i plus 1 factorial has a factor of 2i minus 1 factorial as in it, right? Here it is. Here's 2i minus 1 factorial, which is the whole numerator, right? That's the whole numerator. So we can rewrite this sequence very much more simply as 1 over. So can I write 4i squared plus 2i? And so can you write out what this means for a third grader? So you see these symbols and you think what? You see this? Think what? Go. See this? Think what? Everyone write it down. So we're going to start getting into more complicated, uglier, scarier expressions. Can't lose sight of what it is we're looking at. What does it mean? Tell me what to do. 1 over 6. 1 over 20. 42. All right, that's good. That's what that means. So if we can't answer that question, then all this stuff about sequences doesn't matter, right? So all this other stuff we talk about sequences doesn't matter if we can't answer this initial question of when you see this, you have to know what that means, right? What does it mean? It means a list of values. Let I be 1, that's your first value. Let I be 2, that's your second value in the list. Let I be 3, that's your third value in the list, etc. Okay, and then we talked about another question about this, right? So what was last time? What's something how can we analyze this for what? Analyze this for convergence or divergence, right? Convergence or divergence. Does this converge or diverge? Converges to? Because it's really much like what? So it's like it's similar to a type of sequence we talked about last time. What kind was that? P sequence, right? P sequence. So you can look at this 1 over 4i squared, and we know that that converges to 0 because this is greater than 0. Remember, all it has to be is positive. Remember that? All this exponent has to be is positive. So what about the plus 2i? Well, that just makes the denominator bigger, right? So here's an argument you can make. We know that 1 over 4i squared is a convergent P sequence because 2 is greater than 0. Now this sequence, what? All the terms are smaller because the denominators are even bigger because we're adding 2i. See that? So we're making the denominators, each denominator bigger than 1 over 4i squared. Therefore, all those terms are actually smaller. So certainly that will diverge as well. Okay? Or we just, again, we could just analyze this as a rational function, right? Degree of the numerator is 0, degree of the denominator is 2. Game over, right? The degree of the denominator is bigger. That thing goes to 0. All right, questions on anything so far here? So that's a convergent sequence, 1/6, 1/20th, 1/42, 1/72, etc. We did all this already. Okay, so now we want to talk about, we talked about convergence of sequences. Now what about convergence of series? What does that mean? So an infinite series converges. What's an infinite series? Again, what is that? Take a sequence and do what? Add them all together. That's the way you want to think about it, as simply as you can, like a third grader, right? You got this list. You're going to take all the numbers in the list and you're going to add them together. One big summation, one big sum. So the series converges if that sum of all the numbers in the list is a finite value. If it doesn't sum up to a finite number, the series diverges. Okay, so here's some practice here. Represent the sequence, the series, and the sequence of partial sums using only symbols a third grader would understand. So let's do this one first. So So I want you to represent the sequence, represent the series, and the sequence of partial sums for this sequence CI. Hey, Jillian, how did the sequence go? Can you tell me? 3/2, okay. 12/5. That's good. 40/10. How's that? Is that right? Oh, I just got my switch the numbers there. Got it right now? Sequence, right, is the list generated by that formula. Okay. Milka, how about the sum? Did you write out what the series would represent? This is the series associated with that sequence. Okay, and then the sequence of partial sums, maxim. No, like third grader, for third grader. Three halves. You don't have to do them. Don't try to do adding fractions in your head. You don't have to do that. Just to represent it. Just represent. Yeah. Right. And that's a new sequence, right? For partial sums. Okay. Good on that? Again, this is baseline stuff, right? Foundational stuff. Got to have this down. Sequence, its series, and its sequence of partial sums. All right, so does the sequence converge? Does the sequence converge? And if so, to what value? So this is like a homework problem, right? Or what we did on Monday. So looking at that sequence, how can we analyze that for convergence or divergence? Compare the degrees, right? This is a rational function. Degrees are the same. Therefore, you just look at the ratio of the leading coefficients, right? So that as I gets very, very large, this thing basically becomes 3i squared over I squared, or 3. So we could say the limit as I gets big of Ci is. So go far enough out into the list. So I'm going to actually go to the millionth term, the billionth term, the trillionth term. These numbers are like what? The millionth term of this list. What could you say about the millionth term in this list? Is it 3? Super, super close though, right? And then the billionth term in this list. Is it 3? No, but even closer, right? Again, pick any degree of closeness to 3 you want. As long as you go out far enough, you'll reach it someday, right? Someday you'll reach it, and then you'll be closer after that. Okay, that's what the limit of 3 is. So I'm going to express that like this. Meaning, these aren't really 3s, but they're indistinguishable from 3 at some point. It's just going to basically get to the place where they're just all So close to 3 we can't tell the difference. Okay? So what about the series? So what do we say? The series converging means add all of them up in the whole list and you're going to get a finite value. Does the series converge? Yes or no? Did you say no, Cody? You said no. Why not, Nick? Well said. Did you hear that? That's perfect, right? What happens? We just get a bunch of like virtually 3s. Essentially, they're all 3s forever. So if we keep adding them together, what's going to happen? It's just going to keep adding 3 forever. We'll never reach a finite value. It'll just get as big as you want. Just keep getting bigger and bigger and bigger by 3. Super important idea here. Super important concept. Because the limit of the sequence is going to 3, trying to add them all up is just going to be like adding an infinite number of 3s together. That won't top out, right? That won't become finite. That will just keep increasing forever. Super important concept. And how does the sequence of partial sums relate to the infinite series, which I have covered up there, so I'll go back here. How does the sequence of partial sums relate to the sum of the series? We talked about this a couple days ago. So we said this sum, what, is going to just get really big because you're just like keep adding 3s over and over. So what about the sequence of partial sums? That's a new list, right? What is that list going to do? Is it going to diverge or converge? Diverge, right? It's just going to, that sequence, that list of values is just going to be a list that just keeps getting bigger and bigger and bigger according to adding one more of the sums, because we keep adding 3 every time. So this list, sequence of partial sums, is going to always, the next term will always be 3 bigger than the one before. You just keep adding 3. So you're making this list of numbers. The next one's like always 3 greater, or about 3 greater than the one before. So that will also diverge. Just get infinitely big. Nick? Okay, the sequence. He asked, does that mean that only series that are going to converge are sequences that converge on 0? Bryce likes it. Yeah, this is a huge point, right? This is where we're going. So that's where I'm about, and that's a good, good looking ahead. Was there another question? Yeah.
So for sequences, does it matter if we put converges to whatever finite number, or do we have to use the limit notation? Does it matter?
Just know how to do both.
Okay.
Yeah, so know how to do both. But it's just two different ways to express the same thing. Okay, so let's look at this one now. New example. D, sequence D. Write it out. So let's write out the sequence, series, and the sequence of partial sums. Write that out. Two squared is 2. Come on, don't you know? I'm not very good at math. Okay, does the sequence converge? Certainly. Converges to 0. So this is what? The denominator is bigger than the p sequence with p equals 2. Or its rational function with degree of the denominator greater than the degree of the numerator. So this goes to 0. All right. And so then does the series converge? Okay. So if we were to add them all together, or add all those numbers together, would we get a finite value? We'll take a look at it. I'll give you a picture of that in a second. Okay. And then how does the sequence of partial sums relate to the series, right? So if I took 4/3 and then 4/3 plus 4/6, and then it's 4/3 plus 4/6 plus 4/11, then the sum of the first 4 terms, sum of the first 5 terms, etc. What are all these values related to the sum? So each one of these values relates to the sum. How? And say, what about, in that sequence, what about the 100th term of the sequence? If I take the first 100 terms of the series and add them together, I get the 100th term of the sequence of partial sums. What about that? How does that relate to the series? The sum of the series. So, yeah, say it. Pretty close, right? Pretty close. What about the 200th term? Closer, right? And then the 300th term? Closer. So what we get in the sequence of partial sums is a list of approximations of the sum, and they get better and better and better as you add more on. Does that make sense? Right? Because each time you add more values, you get closer to if you were to add all of them together. So you get a list of a list of approximations that get better and better and better the more you go out in the list. The best approximation you can get is the one that has the most terms added. And then exactly if you could add all of them together, right? All infinitely numbered terms, then gets you exactly the value of the series, or the last term in the sequence if there was one, right? Sequence of partial sums. Okay, so let's take a look at, oh, here we go. So the infinite series converges if the sum of the series is a finite value, and the sum of the infinite series is the limit of the sequence of partial sums. So kind of an important recap here. The series converges if when you add all of them together, you get a finite value. And then the limit of the sequence of partial sums is the same as that sum of the series. Super important. All right, so let's look at this. Seconds. Let's get this GC file here. So here's those two. And so what I'm going to show you here is on the x-axis is the value of I. I equals 1, 2, 3, 4, right? And then the y-axis of these points is the ith term of the sequence of partial sums. The sequence of partial sums. So when I is 1, the sequence of partial sums, we get what? 3/4 and 4/3. 3/4 and 4/3. So there's that's showing that. So then when I equals 2, I'm going to add the first 2 terms of the sequence together. And so let's see. This is the red one. Well, you tell me. So which is the red one and which is the blue one? Is C red or blue? Is D red or blue? What did we say about C? So that one we did before. Eventually, all these terms in the sequence become really close to 3, right? So what would happen in the sequence of partial sums? Each term in the sequence of partial sums is how compared to the one before? 3 greater, right? 3 greater, because you keep adding like kind of one more 3 or something like a 3. Now with the D sequence, we saw that those in the sequence, those are getting small. They're getting to 0. So what we're adding on in the sequence of partial sums is a smaller and smaller number. So again, the y values of these points are the values in the sequence of partial sums. So that first one, it just keeps going up by 3 every time, right? That's C, the blue dots, right? They just keep increasing by 3 every time. But the red ones, because the sequence goes to 0, we're adding on a smaller and smaller number, and it's going to flatten out. All right, and it turns out that, so I made a table here. I'll zoom in on it. So I made a table here, and these are the sequence of partial sums that we found. So by the time we get to 10, when we add up the first 10 terms, it's 3.06. Add up the first 50 terms, it's 3.36. And then I got impatient, so I just started jumping here. So then the first 200 terms to 150 terms were like in the 3.4s. So I just went to 3,000. And so now we see this kind of finally by the thousands, this thing is finally starting to level off, the sum, at about 344. So I have that the sum is 3.443 about. So I'm going to graph that. And so here's where that sequence of partial sums is headed, right? Or in other words, if you were to add together all the terms of that sequence, 4 over I squared plus 2, you'd get this value, 3.443. Okay, does it make sense? Yes, please. The first sequence, 3I squared over I squared plus 1. Remember, what was the limit of that sequence? 3. So the sequence of partial sums, so we're going to add together what? These partial sums. So what was the sequence again? Quick. 3/4. Tell me. 12 fifths. 27 tenths. The first one's 3/2. What's the fourth one? Okay, thanks. All right, so that's the sequence. The sequence of partial sums is the first one's 3/2, so that's the y value of the first blue dot. And then the next in the sequence of partial sums will be the sum of these two, and that's the y value of this one. Sequence of partial sums. Sequence of partial sums. The blue one, the sequence of partial sums for CI. Right. So then this is essentially adding, so eventually we're just like adding 3 every time, getting higher and higher. Yeah?
Do you ever do anything with like a series of partial sums? Or did it just the sequence?
That doesn't make, the series is adding all of them together, so there is no.
No, he's saying if we make a series of partial sums.
I don't know what that means. What does that mean? A series of partial sums? A sum of sums? I mean, that's kind of what you're talking about. You're talking about like this? No, we don't do that. All right, other questions? All right, so where are we here? So, divergence theorem then lets us conclude quickly, like looking at those two examples. It lets us conclude quickly that an infinite series diverges if the sequence has a qualifying feature. And if we're tracking here, should think of what that is. So what would this what qualifying feature would a sequence have that you could just immediately say that series would diverge? You wouldn't even have to do any more thinking about it. So is that? Exactly. If the sequence converges to something other than 0, then what's going to happen with the series? Whatever that finite number is, you're going to just keep adding that number over and over again, or essentially in the end. So it's the same question again. So the series diverges if the sequence that you're talking about does not converge to 0. So this is really powerful because it's like it we're done. We're done with that series. We don't have to think any more about it. If you look at the sequence and it doesn't converge to 0, game over. The series cannot converge. So it's always the first thing we want to check. Yes, please.
What happens if it's an alternating series, like with the negative 1i, 1's
That's alternating series. So it's the same thing. If an alternating sequence does not converge to 0, then the series can't converge. Yeah. Because then think about your sequence of partial sums. This is going to be jumping, right? If you're alternating between two numbers, then you're just going to jump back and forth between two sums, and it will never sum to a finite value. Yeah. Okay, so this is always our first line of defense. You know, like if you don't have a sequence that goes to 0, we're done. Game over. Series can't converge. Okay, so then the question is, if the sequence converges to 0, then what about the series? If the sequence does converge to 0, then what do we say about the series? Converges, right? We saw that earlier. So let's look at the harmonic series. Okay? So we've been using the symbol I a lot, but any symbol is, you'll see J, you see other things too, so it's K often, so I, J, and K are the most common. So let's get used to using something else. So the harmonic series is this. So my first task for you is, you see this, you think what? You see this, you think what? Go. See this, think what? May, can you tell me? See this, think what? So like it's a list? Is it a list? So it's based on that list, but this isn't the list, right? What is this? So this is jumping right to the series based on that sequence that you're telling me, right? So the sum is when we add them up, right? So this is jumping right to the series for that given sequence. So it would be what you said, but then they'd be all added together, right? Yeah. Right. 1 plus 1/2 plus 1/3 plus 1/4. Okay, what kind of sequence is that? 1 over J. What kind of sequence is that? P sequence with P equals to 1. It's like 1 over J to the 1, so this is a P sequence. The harmonic series is a special P sequence. And does it converge or diverge? Converges because 1 is greater than 0, right? As long as that exponent, that P exponent is greater than 0, that sequence, that's a P sequence that converges. So we know that the sequence 1 over J converges to 0, right? So divergence theorem doesn't apply, okay? Because we know this goes to 0. All right, so does this series converge? Does this series converge? All right, I already answered that. So since the sequence converges to 0, we can conclude about the series? Converges to something, right? Let's take a look. So I'm gonna put this series up here, and we're gonna compare these two. Okay, so notice that these are the same. So we're the same so far. These are the same. So after the first two, we're at 3/2 or 1.5. Okay, now instead of doing 1/3 plus 1/4, I'm going to do 1/4 plus 1/4. What does 1/4 plus 1/4 equal? 1/2. And how does 1/2 compare to this little partial sum right there? Pretty close, he says. Is 1/3 plus 1/4 bigger or smaller than 1/2? Think about pizza, and you'll get it right. All right, okay? You'd rather have a fourth plus a fourth or a third plus a fourth? You'd rather have a third plus a fourth. That's bigger, right? A third plus a fourth is more than half of a pizza or a pie. Okay? So now, instead of doing 1/5, 6th, 7th, and 8th, I want to do 4 1/8ths. And 4 1/8ths equals what? Another 1/2, right? So how does a 5th plus a 6th plus a 7th plus an 8th compare to 1/2? Greater. One more time, or in fact, lots of more times. I'm going to take the next 8 terms, and instead of having them be from 1/9 to 1/16, I'm going to have them be 8 1/16ths, which equals 1/2, which compares how to the next 8 terms here? Greater than 1/2. And then I can always take twice as many terms as I did before and get these to be a half. Does that make sense? So I can take the next 16 terms of 1/32 and get a half. And I can always do that. And I can always take the same number of terms in a harmonic series and show that that sum is greater than a half. So I got 1 plus a half plus something greater than a half plus something greater than a half plus something greater than a half. And I'll never run out of terms, so I can always take twice as many and get something greater than a half added on. Conclusion? What about the harmonic series? What's that? Diverges. Why?
Because you're never getting smaller. You're always getting bigger. Despite it still being 1/2 or greater than 1/2, you're always getting bigger.
I can always find a group of terms down the road that are sum up to greater than a half, and I can keep doing that forever by just doubling the number I had before. And I'll never run out, so I can always double the number I had before. So this is showing that the harmonic series diverges. You see that? Uh-oh. Right. Right. We thought it would converge, right? We thought that if the sequence converges to 0, then that would mean that the series would converge. Were we right? No. So instead, we have to kind of change our hypothesis here. If the sequence converges to 0, then what? What about the series? It may or may not. You're telling me there's a chance, right? It may or may not converge, but we don't know. So this is where it gets interesting, right? So if the sequence doesn't go to 0, it's like that's a trivial kind of series. It's just going to add up to, it's going to get really big. So the problems that we're going to look mostly at are the ones where the sequence does go to 0. And now we have the question, will it converge or not? We saw that the one example earlier, it converged to 4.3 or something like that. The harmonic series does not. It's still, even though the sequence goes to 0, it still blows up. It still gets infinitely large, the series. So conclusion. If the sequence converges to 0, then this corresponding series might converge. Maybe, maybe not. Now you're going to do further analysis to figure it out, like we did here. Makes sense. Any questions? Right. So there's you've got a whole bunch of sequences that go to 0 that sum up to a finite number, and then a whole bunch of sequences that go to 0 that still sum up infinitely. And so that's a big part of what we're doing in the next couple weeks is figuring out, does the series converge or not? All right, so P series. We call the P sequence converges for P greater than 0. 1 over I to the P converges for P greater than 0. And we just showed that if P equals 1, the series diverges, right? So what if P were less than 1? P is less than 1. Then what about the denominators compared to the denominators of the harmonic series? So here's harmonic. What if I did p equals 1/2? The square 1 over the square root. So that'd be 1 over 1 plus 1 over radical 2. How about that series? How do all these compare? So what about 1 over the square root of 2 versus 1/2? Which is greater? I'm giving you smaller denominators, right? By taking the square root, it makes my denominator smaller. So what about those fractions? These are all larger. So if you take a p-value less than 1, we know that p equals 1 is divergent. And if you take p less than 1, it makes all the corresponding fractions bigger. So what about p less than 1? Divergent, right? So anytime p is 1 or less, your p series will diverge. All right? And we saw an earlier example where p was 2. And what happened with that one? Right? We saw an example close, something like that. Where it's like, what do we have? Something over I squared. 4. So this is essentially a p sequence with I equals 2. P equals 2. And what was that? That one converged. Okay? So this 1, this value of 1 is the breakpoint. If you're greater than 1, if p is greater than 1, then the p series converges. If p is 1 or less, then the p series diverges.